Yes, members and friends to our PCS IBS seminar. Today we have a great pleasure to host Professor Robert Shekhter from University of Göteborg, Sweden. And our scientific host today is Sang-Hoon, who will introduce our speaker.
Thank you. Hello, I'm pleased to introduce today's speaker, the Robert Shekhter. Many of you already know him, but I will briefly introduce him for some of you who don't know him well. The Robert Shekhter graduated in the Kharkov University in physics in 1970 and completed a PhD in 1977 on the study of charge quantization and the current states in the granular media, and got the habilitation degree from Higher Attestation Committee of the Soviet Union in 1987. And after the PhD, he continued his research in theoretical department of the Barikin Institute for Low Temperature Physics and Engineering as a junior research scientist, senior research scientist, and the reading scientist officer there. And then moved to the University of Gothenburg, and now he's the professor of emeritus at the University of Gothenburg. Also, he did, for the last 30 years, he did many active research activities. Some of them includes the prize for the discovery of new type of non-equilibrium charge distribution in point contact at low temperature from some Soviet Union in 1993, and he's also was the member of the editorial board of low temperature physics since 1998. Also, was the member of the condensed matter physics board of Swedish Research Council. Since 2017, as a convener of our advanced study group, he actively have been in collaboration with many TCS members. His research interest covers the various fields in theoretical fields, including some electron transport in metals, semiconductors, magnets, and small conductors. Recently, he did, His research topic includes the fundamental properties of strongly correlated electron systems, superconductivities, nanoelectron mechanics, spintron mechanics, optics, and the magnetic properties of nanocomposite materials. So I'd like to let you know one thing, that he's the oldest guy among us. Right, so he's the heart of hearing. So today you need to use the microphone today to ask a question. I will be in the back seat, and please raise your hand. I will bring you this microphone. So let's welcome the speaker.
Thank you very much for a nice introduction. I am the oldest person here, and I must mention that this year we are celebrating 50 years since my second publication was done. It was on point contact spectroscopy, and I will use this in my presentation, the information about these point contacts. I would like to start my presentation with a preliminary remarks, which will probably help us to explain motivation for the research which I'm going to tell you. I will start with a very general statement, an obvious statement that large variety of electric and magnetic properties of metals originate from the fact that electrons are quantum particles which have an electric charge E and have internal degree of freedom, which is a spin. So these two things are on a basic level determine a large variety of metallic, electric, and magnetic properties. For example, if you're thinking of conventional superconductivity, the fermionic nature of electron play a crucial role because it enables Cooper instability in the metals, which transforms usual ground state of the metal into ordered state of electrons in superconductivity. However, if one think how electric and magnetic properties are transformed during the superconducting transition, one can find a great asymmetry in this behavior. With respect to how electronic charge and electronic spin contribute to macroscopic phase coherent phenomena in a superconductor. The large variety of fascinated properties of superconducting can be seen as a manifestation of electronic charge. It's a charge phenomena of coherent electrons, ordered electrons in superconductor. A number of such a phenomena can be mentioned. At the same time, no significant contribution of electronic spin degree of freedom can be seen in the properties of superconductor, BCS superconductor, conventional superconductor. And this fact is actually very simple manifestation of singlet pairing of electrons in a superconducting state, which actually lock electronic spins and making the charge carrier in a superconductor to be spin zero particles. So there is no room for spin to play in this case. Could you switch it? So this is why we can ask the question, may electronic spin ever show up in BCS superconductivity? Could we activate electronic spin and unlock this spin to make electronic spin degree of freedom participate in phase coherent phenomena? The positive answer to this question has to do with answering whether or not it's easy to polarize superconducting Cooper pairs, spin polarized. And we can just make a simple estimation, what is it easy or not? We can use external magnetic field, for example, to polarize spin-neutral Cooper pair. And in order to get it, we need a magnetic field, which will be of the order of coupling energy of Cooper pairs. And we get magnetic field for typical superconductor, a few Tesla. It's a huge field for superconducting. Much smaller fields will destroy superconductivity just because of diamagnetic screening of the magnetic field cost energy, and it's too much to consider for superconductors. So there is a thermodynamic magnetic field actually which destroys superconductivity due to diamagnetic screening. And this estimated spin polarizing magnetic field is relativistically large as compared with this thermodynamic screen. So we never reach such a magnetic field. And conclusion is that the binding of electron into pair is too strong in superconductors. And it's not easy task to spin polarize such an entity. Of course, one can play with this and try to suppress a coupling energy in a superconducting Cooper pair. There are several ways to do this. And one of the ways is to just let supercurrent flow through the system. And we know that depairing phenomenon occur. There is a critical value of velocity where superconductivity disappears, is suppressed. But of course, we can, if a suppressed coupling in the energy, the electrons become easily polarized in spin, but then we destroy superconductivity. It looks like to have a very well-established superconductivity and to have highly polarized, spin-polarized electron is a contradictory conditions. You cannot have both. You cannot have both established superconductivity and easy polarized by spin electrons. And the question which appears is there a way around of this contradiction? And could we still arrange the situation when spins of Cooper pairs can be polarized? And this is my subject of my talk today. And the way out is to consider non-homogeneous superconductor. Suppose that we have point contact. I just mentioned this in the beginning of the talk. We have dielectric screen which separate two superconductors and not prevent current to flow through this screen. But there is a hole in between this screen which allow certain current flow through this orifice. This is a point contact. And what we know from the point contact is that current become concentrated around this orifice, and high current density will occur in the vicinity of this microconstriction. And suppose that current is such that current density in the middle exceed critical value, and we have a superconductor, we have normal metal here, while in the environment outside of this microconstriction, we still have superconducting pair. This makes electrons here easy to polarize because we don't have any coupling in this area. Does this mean that we will destroy superconductivity in the system, global superconductivity? And answer is no. And the reason for that is proximity effect. The Cooper pairs built here in a superconducting area may penetrate this normal region and still keep phase coherent, global phase coherent built in superconducting, although there is no coupling between electrons anymore in this area. And this phase coherent can be preserved until these electrons enter another superconductor. This is proximity effect, which keep global superconductivity working. And this brings us a hope that if we will let Cooper pair enter a normal region, polarize Cooper pair here, and then inject this spin-polarized Cooper pair into superconducting, we can have net spin polarization of BCS superconductor as a proximity effect. Now, proximity effect will work on another side of the interface. It will work on superconducting. It will create a spin-polarized Cooper pair in BCS superconductor as a proximity effect. This is a hope what we can get here. And this situation is typical situation for Josephson effect, when we have current flow through the non-superconducting region in the material. And this would be essence of my talk, that we do have possibility to have non-zero magnetization in a BCS superconductor due to injection of spin-polarized Cooper pairs. And this polarization of Cooper pair we will consider to be as a result of spin-orbit interaction in this area. We can, of course, discuss how magnetic field may polarize electron also, but then it will be not so attractive for us because we need to localize this spin-orbit interaction this interaction in a small region, and it's not so easy to localize magnetic field in a small region of the material. But spin-orbit interaction is electrically generated phenomenon, and this is why it can be localized here. And second circumstance is that we can design spin-orbit interaction by using electrostatic and I will say some mechanical forces to control spin polarization of Cooper pair externally. So it's easily tunable device. So now I say that the talk is, I explain the title of the talk. We will talk about the tunneling through the electric weak link, superconducting weak link. It means that there is part of material which is non-superconducting. And we will see the effect of spin-orbit interaction for such an injection. So the paper was done by, in collaboration with my many years collaborator, Ora Enkin-Volman and Amnon Aroni from Tel Aviv University, and Mats Jonsson, my colleague for many, many years from Sweden, from Göteborg University. This is outline of my talk. I will start with a description of the experimental test setup which we suggest for making this job, which is based on experience in working with the point contact in Kharkov. And then I will briefly describe the introduction into Raspberry interaction in the spin-orbit interaction, and I will stress on semi-classical interpretation, which is useful for our interpretation of this phenomenon. Then I will show how this interaction results in polarization of normal, spin polarization of normal electrons, which are penetrating through this big link. And then, as a result of this polarization, we will come to the picture how Cooper pairs can be polarized by injections of the photon. And then I will discuss some spintronic application of this net magnetization which occur in such a superconducting device. Okay, so this is a setup which actually actively used in Kharkov and many other places when they study so-called point contact spectroscopy in metals. That was 50 years this year since pioneering work done by Igor Janssen in Kharkov. He showed that using a point contact like I described make such a high concentration of electric current that electrons get very highly energized. So we have highly energized electron, which extra energy can be controlled by voltage applied to the point contact. And this electron can be employed to spectroscopy elementary excitation in the metal. This was the essence of point contact spectroscopy, which was used widely by studying phononic spectrum, magnonic spectrum, and other excitations in metal. So the configuration which they use usually for heavy point contact with controllable resistance is break junction configuration. What break junction means? Suppose that we deposit two metals here on a substrate which can be bent mechanically. If you bend this substrate mechanically by loading, like it shows here by error, the device, we will control distance between these two gap between these two metals. And this is how you control resistance of the tunnel junction between two metals. We suggest to use this configuration, which people use, just to study effect which we want to describe. To do this, we short this device by nanowire here, which use these metals as a support. And by changing the bending of the wire, we change the bending angle of this wire. And as we will see, the spin-orbit interaction is crucially sensitive to curvature of electronic trajectory. And this would be the way how we control spin-orbit interaction in this system, in addition to electrostatic generation of spin-orbit if you use a gate electrode. So this is a device.
This device was realized in '74?
Without this wire.
And has this been done more recently?
No, it was not done. I just was on conference in Kharkov, which was devoted to anniversary of this point spectroscopy, and I suggest them this configuration. It was some discussion. Okay.
Sorry, one question. You bend the substrate and the nanowire.
Yes.
If you bend the nanowire only without bending the substrate.
But how I will bend it? Okay, in principle, if you put very high electrostatic charge here, you can attract this wire and deform it mechanically, but I think it's a little bit exotic.
I see.
Okay, so what is important for us, and we will show later a little bit, that this device serves as a spin splitter device. We will show that a large quantum fluctuation of the spin occur here, which are controlled by bending and of the wire and this. And this spin fluctuation means that incident of electron with a given spin projected actually reflects and transmits at a superposition of spin up and spin down states, because no spin projection is conserved here because of the spin orbit interaction. There is no conservation of any spin projection. This is why I say quantum fluctuation of the spin. So, and this actually bring electron into superposition of spin up and spin down as a result of this scattering. And the same effect appear if you have pair of electrons going through this system. Each of component of this pair actually will be brought into the superposition. As a result, as we will see, a superposition of Cooper pairs, spin polarized up and spin polarized down, and singlet Cooper pair will appear as a result of such a scattering. So, and we will have such a conglomerate of the Cooper pairs differently polarized. And what moreover, that we will see that controllable way of doing this fluctuation results that net magnetization appear in this spin fluctuation system. It's regular action on the electronic spin, and net magnetization appear, which determined by design of spin orbit interaction here inside.
Can you explain again why you need this wire? Why do you need this wire?
I need, in order to get, later you will see, in order to get a really strong spin orbit interaction.
So this must be a good, proper material for which you have strong spin orbit. Is that what you know?
In principle, Rashba spin orbit interaction can be generated by any electric field, even for any material. It's not a property of material, it's a property of external electric field. I will tell you in a second how it will appear. But of course, you need to make it strong effect, you need certain material constant of this. For example, carbon nanotubes are known for strong spin orbit interaction inside, so it can be used here for shorting of this device. Okay. So what is a spin orbit interaction? I will employ a semi-classical picture of spin orbit interaction because there is a classical analog of spin orbit interaction in physics. And it is formulated like this. If it's presented here, so we have particle moving along certain trajectory and carrying magnetic moment mu. If this motion takes place in the presence of electric field, which is generated by certain charge, then such a motion will generate spin precession of magnetic moment. This is essence of classical essence of spin orbit interaction. Motion, trajectory motion generates spin precession if external electric field is present. Physics of this is very simple, and it comes from the fact that we go to the reference system associated with a movable particle. Then charges which are generated electric field will create a current here in this reference system, and this current will generate magnetic field. And magnetic moments start to process around this magnetic field. So this is the physics of spin-orbit interaction. This is classical analog. Of course, to apply this for electrons, we need to have a fully quantum mechanical description of this phenomenon. And moreover, we have to have a relativistic version of this description, because spin by itself is a relativistic phenomenon in quantum mechanics. It turned out that this energy, which we calculated for precession of magnetic moment, is still valid in this case, with the obvious replacement that instead of magnetic moment, we should put operator of magnetic moment of spin, which is actually Bohr magneton multiplied by spin operator, or sigma spin operator. Further generalization of these things become possible if you consider electrons moving in solids, inside of solids. Then electric field produced by lattice, crystal lattice, should also be taken into account. And it's for lattices of certain symmetry is breaking, like inverse spatial symmetry is broken, then effect of crystalline field will produce additional spin-orbit interaction, even in the absence of external electric field. Second effect appearing in solid state is we should replace this mass by effective mass in a solid. And for certain materials, when we have a very small effective mass, we can significant increase of this interaction. We can have effective mass 2 orders of magnitude smaller than electronic. And this will compensate us, partially at least, this relativistic smallness of the effect. The effect is 1 over c squared, because of some Bohr magneton is 1 over c, and this is 1 over c squared. Okay, so this is in this paper, it was proven that quantum mechanical treatment gives the same result, and Rajba introduced in solids, generally for the solids, in external magnetic field, and Janet Gresselhaus considered effect of crystal lattice on this effect. So this is spin precession is a main feature which we will use and employ many times in this presentation. Now, how electron is transferred through the channel with the spin-orbit interaction active. Semi-classical picture would imply that particle with magnetization, say, orienting up, incidenting channel here and start to move along the channel. If electric field is oriented vertically here, then magnetic field, effective magnetic field, which generates spin rotation, will be perpendicular to the screen. So the magnetization start to precess while moving through the screen. So there will be some precession, and when we go outside of the channel, we will have orientation of magnetization generally different from what we have here. So we polarize the electron in different direction in this case. That's called a semi-classical picture. And quantum mechanical picture is such that we consider quantum states propagating plane wave with in a spinor states up. And since no conservation of spin occur here due to spin-orbit interaction, we have superposition of these 2 states characterizing up and down states inside the channel, and coefficients will be determined the same semi-classical rotational length. It's actually, this propagation is associated with Rabi oscillations of the electronic states here. Again, we come out of the channel with a superposition of spin up and spin down states, which oscillatory depends on length of the channel, because it's a sort of precession. And it's interesting then this phase, which is classical precession phase, actually have a quantum mechanical meaning. And this meaning may appear in the following consideration. At the interface, we have to match incidental waves of electron to the state here. But because in this channel we have jump in energy of spin-orbit interaction, in order to keep total energy the same, we have to have jump in momentum. We have to have a jump in kinetic energy of electron, to have both spin-orbit energy and kinetic energy the same. And this extra shift of momentum here will result in accumulating of extra phase while propagating. And this extra phase will depend on spin-orbit interaction and comes from the matching condition. And this accumulation of the phase is very well known Aronoff-Kasher effect, which I will just present here. So if you do these matching conditions and so on, we will find that extra phase, which are accumulated due to spin-orbit interaction, while propagating along certain trajectory, is given by such an exponential factor here. Of course, it's operator, and this is spin operator here, but it's extra phase factor due to spin-orbit interaction. And this is how, and this is essence of Aronoff-Kasher effect, that wave function of electron accumulate extra phase if electron moves in an electric field due to existence of electronic spin. And this effect is dual to the effect of Aronoff-Bohm effect, when wave function of electron accumulate extra phase if it's moving in magnetic field instead of electric field due to electric charge. So it's a dual effect. Aronoff-Kasher effect is dual effect of Aronoff-Bohm effect. And this is main conclusion which we want to utilize in considering the transports of our system. We say that transferring of electrons through the spin orbit active area results in accumulation of extra phase here. An extra factor should be taken into account in transferring amplitude of electrons to such areas. Now we are preparing for considering transport in the system. And we will use.
Sorry, may I ask you a question? In your previous slide, before, here it seems that in this semi-classical picture, the spin orbit coupling in this nanowire rotates the spin, and it seems that you already have enough property to manipulate the spin. But at the beginning, you show me this the bending nanowire.
Yeah.
So
I will come to this. You asked the question. This is straight wire.
Yes.
And I will come to this later.
Oh, thank you.
Bit, just in a second. It's non-trivial question. So, but just in a minute, I will come to this. But we use transport in such a system in using tunnel Hamiltonian approach. In this approach, phenomenological approach, we say that we destroy electron in one lead and create instead electron in another lead. And intensity and amplitude of such a problem is actually transferring amplitude for electron to transfer from one lead to another. So this is tunnel amplitude you introduce. What we can do here is to say that if in addition transfer goes through spin orbit active area, additional phase factor should appear in tunnel amplitude. It's a phase accumulated due to propagation in spin through the spin orbit area. Of course, it's according to Aronoff-Kasher effect is integral over trajectory. And if trajectory is bent, it's a non-trivial problem to calculate this because of non-commutative of the spin orbit part and different part of the trajectory. So in order to avoid this and to catch the main feature of the effect, we consider simplified picture of electronic transfer through the weak link. We consider that this is trajectory of electron in a real space shown here. We model motion through the bent nanowire as a two straight segment, which at certain point are join each other. And this joining point, bending point of the trajectory, we can consider as a scattering of electrons when electron change the momentum here from this to this. So this is semi-classical, and this is semi-classical, but this is where semi-classicity is destroyed. So in this sense, we can easily calculate everything, because in lowest order in transferring, the transfer from left to right is actually product of three propagator. One is Aronov-Kasher propagator in low straight channel, then scattering, transferring amplitude, and then Aronov-Kasher propagator through another channel. So we have the Aronov-Kasher factor actually is a product of these two exponential factors for straight channel. Then everything can be easily calculated. These two are not commuting with each other, it's very important. So, and we can calculate this Aronov-Kasher factor, and this is the result here. What we can see from this result, first of all, it's expressed in terms of sigma component of sigma matrices here. And in addition to diagonal component in representation of incident in spin, diagonal elements of this matrix, first and third element. We have sigma y here component, which is non-diagonal. And this non-diagonal sigma y describing fluctuate electronic spin. So we have two channels for tunneling for transferring of electron. One is without spin flip and one is with spin flip. And interference of these two channels actually produce the main effect in superconductivity. Then we can see that how crucial is bending of the nanowire. The contribution to this spin flip crucially depends on bending of nanowire. So geometry or mechanics will determine spin flip processes in our device. We load it mechanically, but we manipulate with electronic spin. Okay, so this is tunneling of normal electron. One electron, and then this is tunneling amplitude. Now we can employ this picture to consider superconducting properties of the device. And this is a scheme what we consider. We consider two bulk superconductors, which connected with non-superconducting material. And we consider electric field which generates spin-orbit interaction. So it efficient Rashba field, Rashba magnetic field will be oriented perpendicular to the screen, which will destroy or disturb spin states propagated here. And this distortion is described by Aronov-Kasher factor. What is important, I already mentioned several times, the dynamics of this propagation here is not affected by superconductivity, especially in the limit when this length of this channel is smaller than coherence length in the superconductor. So this dynamics is essentially the same as in a normal metal. And everything is like this. We prepare everything, every spin configuration, and then deal with what we have on the exit here. It's a proximity effect, spin proximity effect in a superconductor. Okay. So the standard scheme, I mean, for considering, it's a standard scheme, I mean, to calculate Josephson effect in this case. We're talking about ground state of isolated superconducting, which is BCS state, which made of pairs of electrons here. We have isolated superconducting diagonalized in terms of Bogoliubov operators gamma, which are shown here. I will not go to details of this. And in addition, we should, according to prescription, add to this tunneling of single electron given by tunnel Hamiltonian, with all this that you already derived. So what would be the effect of this on whole picture here? This is our task. Yeah. Okay, this is scheme how everything is work here, how the transfer of Cooper pair take place here. For comparison, I will employ this again, semi-classical picture to make it more easy. In a normal metal, non-superconducting, plate A here. In normal metal, we already discussed that electron with momentum polarized in up direction rotates while propagating through the spin orbit active area, and its polarization becomes shifted by certain angle. Now, how it will affect transferring of Cooper pairs? Hamiltonian, tunnel Hamiltonian, transfer only single electron. In order to tunnel two electrons, we need to have two-step tunneling process. And these two steps are presented here, 1, 2, 3, 4 stage in this tunneling. We start with the Cooper pairs which are situated here. We break this Cooper pair by destruction of electron by tunnel Hamiltonian, destruction of electron in Cooper pair, and create quasi-particle excitation in this, and take another electron to be transferred through the system. And this transferring is actually very similar to this transferring. It rotates spin, and we get electron arrives here with a certain shift of momentum. Now it's turn to transfer second electron as an intermediate process in tunneling. Then it's very important that Cooper pair is made of two electrons which are in states which are time reversed to each other. And it means that dynamic of this electron should be time reversed to the dynamic of the first electron. It means that spin down should rotate counterclockwise instead of clockwise. And we see that this electron, we have another electron which arrive here counterclockwise, and they become non-parallel to each other. The Cooper pair become polarized, and extra momentum appear here. This is the picture of spin-polarized electron. Of course, it's a semi-classical picture. One has to consider coherent mixture of spin-up and spin-down states. And this very configuration should be interpreted like we get at the exit coherent mixture of singlet and triplet, and we should put one more states oriented down. Spin up and spin down triplet states, and singlet states goes in superposition. So this is how superconducting condensate become fluctuating in spin. So this is a picture of the transferring. And we can calculate easily, for example, current, supercurrent in the system, perturbatively using second order in tunneling, using this standard definition. And this is what we directly go with calculation, and we get the following results for supercurrent. Critical current, it still depends on superconducting phase difference, sinusoidal, but critical current is given by this formula. So we can see that spin-orbit interaction, which is represented by this term here, actually diminishes of spin current, Josephson current. And it has a simple explanation, because we have, without spin-orbit interaction, we have singlet Cooper pairs going through the system and contribute. Now, fraction of this Cooper pair get spin-polarized. And they cannot carry current, because current inside of superconducting can be carried only by singlet pairs. And this is why we diminish number of singlet Cooper pairs, and we diminish the current here. And this diminishing effect, again, depends on bending wire and strength of spin-orbit interaction, which is actually Aronoff-Koshar phase here. So we have this field, and it's very interesting that spin polarization of Cooper pair manifests itself in diminishing of the current, because some spin polarized Cooper pair get out of counting of supercurrent flow.
May I ask my question here? You show on a plot that the current has the same. You show on this plot that the current with this tunneling has the same sign with just Josephson current, But I see that, for example, if θ is 0, then we will have a negative current and
No.
so does it has, just a simple question, does it have sense to put θ equals 0 here to this equation and have
What was C?
θ angle?
Theta.
Theta angle.
Theta. Okay, maybe this is something where I need to consider. There was no such a thing that you can reverse it. It's this factor 2. I have to have a look at this. You mean that?
Okay, yeah, because I mean that you can have negative coefficients there, yes.
I don't see this possibility here. I think it's some mistake. Sorry for that. Okay, now comes a more interesting case when we can test not only number of singlet pairs like supercurrent test, but we can test non-diagonal element of density matrix. Because of fluctuation of spin, we have not only diagonal elements, which are singlet Cooper pairs in a representation of native Cooper pairs, but also some magnetized Cooper pair, which is non-diagonal in spin. And this is magnetic moment, which we calculate. It's determined by sigma components of sigma matrices, and for X and Y components, we have non-diagonal contribution. It means that this magnetization scan non-diagonal component of density metric, because in order to get non-zero average here, we need to have density metrics also non-diagonal in addition. So this measuring of magnetization scan non-diagonal element of density matrix. How it works? Suppose that we have Cooper pair here. So one single spin flip will transform singlet Cooper pair into triplet Cooper pair. And depending on what electrons flip its spin, either down or up, we can have either triplet up state or triplet down. So we have superposition because we have superposition of such a tunnel. And this flipping will result in that magnetization. Okay, so this is the result also, nothing to tell in between. You just calculate in second order of tunneling this, and you get the magnetization, which is of the order of Bohr magneton, then transparency of the channel and number of channels, transporting channels here, and then this vector W, which determines how effect. I mean, how effect depends on tuning parameter in this case. First of all, very significant part. This magnetization is actually also Josephson-like dependence, superconducting phase difference. So it's purely superconducting properties of the material, which depends on superconducting phase difference and obey all interference effect and all this thing. For example, if we bias our junction, this phase starts to depend on time, and this magnetization will oscillate in time. Here. Secondly, orientation of this magnetization determined by these coefficients alpha and beta. This is odds in y and x direction. And depending on bending of the wire, we can orient this magnetization differently in space. So it can be highly tunable orientation of this magnetization. And also the oscillatory depends on strength of spin-orbit interaction, which is a gate effect of electrostatic field making this. So we come to the conclusion that there is a Josephson originated magnetization, spin magnetization. BCS superconducting can be polarized spin, can be polarized in spin. And this polarization is very flexible by changing either voltage or some electric field or bending. We easily really may design magnetization distribution here very easily. Okay, so what we come to what the picture is? We say that we dealing with the transferring of two electrons, Cooper pairs of the junction. Each transfer of this electron can go with two channels, either no spin flip or one single spin flip. So if we transfer two electrons, we have four different channels of tunneling. And they can be separated in two groups. One group I call it singlet providing tunneling, when either no spin flip take place due to tunneling or double spin flip take into tunneling. Both these channels keep singlet pairing of electrons through the channel. This would determine diagonal part of density matrix here and will contribute to the current to the system. There is channels which correspond only single spin flip process, and it results either with spin up polarized Cooper pair or with spin down polarized, and they go in mixture because of this channel interfere with each other. So this will not contribute to the supercurrent, but will contribute to the magnetization of the system, because this kind of things, because of coherent mixture, we have non-diagonal elements of density matrix here. So, and we have, so to speak, what we call spin-charge separation here. We have two different sources for charge flow and magnetization flow. Charge flow is determined by diagonal component of density matrix, and spin flow or magnetization determined by non-diagonal component of this. And measuring of charge current and magnetization make you scan diagonal and non-diagonal components of density matrix. And this result is result of such a scanning here. So this is what both effect represent effect of spin polarization, but Josephson current indirectly represented because we have partial diminishing of singlet Cooper pair. Okay, so we have, as a conclusion, we have magnetization as a totally superconducting property of species superconductor, which is highly tunable, which may produce two effects. First of all, this magnetization may affect superconducting properties itself, because such a magnetization should imply that Meissner current should appear. This magnetization should be screened by superconducting current, and this current can be detected. So this is the way how you will detect this magnetic structure. And another thing is that magnetic structure itself is highly tunable by external fields. And the way how it's affected by external magnetic field goes through three phases here, which are essential for the phenomenon. It's superconducting phase, Aronov-Kasher phase, and depending on topology, Aronov-Bohm phase here. All three phases determine sensitivity of the magnetization to external magnetic, electromagnetic, and both electrostatic fields. And one could imagine different kind of application of these things. First of all, one can think of spintronics of Josephson junction. Now, in addition to, we have no spin playing a role in superconductivity. Now we have active role of electronic spin in the superconducting property. For example, in Josephson electrodynamics, magnetization should be involved through this phase, which includes the dependence of magnetization of electromagnetic fields, and so on. So there is some effects which can occur due to this magnetization. One can think of how squid interferometry and the small rings reacting on external magnetic field would be modified by spin polarization if you have this spin orbit active junction. Then, of course, interesting properties are arrays of Josephson junction of spin orbit. We have actually each junction produce magnetization, and we have interference between this magnetization, which is controlled by phase. So everything is so planar or sequential arrays. Very interesting subject is here how Coulomb blockade, how at all electron-electron correlation would affect all this phenomenon. And we know that we already see the effect which could be. We know that there is in Coulomb blockade, in superconducting Coulomb blockade, there is a, so to speak, charge qubit states. When we block electronic Josephson transport through the Coulomb dot, allowing only one single Cooper pair to tunnel with this. And usually we have qubit states which we have superposition of no extra Cooper pair or existing Cooper pair on the dot. And this is qubit state. Now, what we have qubit is actually extra Cooper pair which can be spin polarized due to this tunnel. So we have the qubit which has spin label and charge label to this. So this could be transducing of or transferring spin and charge information in this. But would be needed to consider this. And microwave properties of the system are very important. So this is a program we are working on some of these directions here. And I am coming to the conclusion, which I stated here. So thank you very much.
Okay, do we have any questions from the audience?
So you need this wire only for
To make a single trajectory.
to make a curved trajectory.
Yeah.
So why do you need a wire at all? Maybe you can just
We have this propagating modes along the channel, which mechanical constraint of electronic wave along the channel make it go along the trajectory. I want to think of this, maybe we can
probably other ways then because of
in magnetic fields the curved trajectory of electrons.
Yeah, but you
cyclotronic trajectory of electrons.
But you wanted to do
Magnetic field, yeah.
So in the beginning of the talk, when you showed the device from Kharkiv, how do you do spectroscopy with it?
I can tell you, it's interesting. So, if you consider current flow through the orifice, so the microconstriction, you will have, and you have no relaxation. You have only electric field applied here, which potential drops actually on the orifice area. So electric field accelerate electrons. And because electric field is located by the constriction, electron get full potential drop going through the and goes with extra energy inside the atom. What happens then? This extra energy can relax. Electron can emit photon, can emit magnon, and so on. And by this emission, you create backflow current. You emit photon, change momentum, and go backwards. This would diminish a current. And this would mean that you have nonlinear in voltage contribution to the current. Usually it's linear, and this nonlinear contribution. But we actually working with Janssen at that time and developed the theory. We show that second derivative of a current voltage characteristic is proportional to spectroscopic function of emission of these photons, and it's proportional to density of dynamic states and so on.
Can you comment on the magnetization profile of this Josephson-Johnson arrays?
Comment on what?
More on the magnetization profile of Josephson-Johnson arrays, like how you mentioned in the previous slide that one could think of this Josephson-Johnson arrays.
Josephson
Junction array.
arrays. Okay, this is interesting. I probably need. Maybe it's difficult. So if you have planar Josephson junction and you put magnetic field, now I want to employ magnetic field, parallel to this plane of the interface between superconductors. This magnetic field would generate Meissner current in the upper part to the right and down part to the left. It means that phase difference at given point will depend on position of the dot. And it means that if you put several spin orbit active junction, this phase difference from each of these junctions will be different, depends on spot. And because of sinusoidal dependence on this phase difference, we have interference contribution from many of these channels, which results in peculiar dependence on external magnetic field. This is one idea.
Thank you.
Do we have any further questions from the audience?
Because there is an electric field in the system, you used this effective tunneling way to describe this problem.
Mm-hmm.
Can one think of it in terms of Landau's inner problem?
Those inner, you have to have a breakdown.
No, because you have, I want to have a Hamiltonian which is linearly time dependent.
Linearly time dependent.
Yeah.
Definitely we will have. By the way, actually, what we are doing now, we consider that electric field, which induces spin-orbit interaction, actually is induced by microwave field, so it's time-dependent field. So you have inelastic channels of absorption and emission of these phonons.
Okay.
And then it's interesting effect because it depends on how polarized your microwave is. For magnetization, it's very important. Is it linearly polarized or circular polarized?
Mm-hmm.
All this spin effect would depend on this. So say this.
Do we have any other questions from the audience? From our online guests, do we have any questions? No, seems not. So then let us thank Professor Shekhter for this excellent presentation.